Now I will just move to an offline version of that sketch, which is freely available, and this is not a perfect sketch, but just a suggestion of what could be done in the early grades in the primary school, where I would suggest that students be introduced to a square and a rectangle with an activity perhaps something like this. A figure that looks like this is called a square. No attempt at a formal definition, because a formal definition would be meaningless to students at this level. They are at the visual level, and it is no point in talking about its properties. By then clicking on these buttons, students can develop, hopefully, a better, richer understanding of a square as something that can be in different orientations and of different sizes, not only in the standard orientation that looks like this. Now, if we look at the rectangle, we can do the same thing, where students can view an animation of it in different shapes, different sizes and orientations, but also noticing that a rectangle sometimes can look like that. And we can clearly see there it is almost a square, or it looks like a square. So that from the start we try and lay the seed for a class inclusion. If we wait too long and they only develop an idea of a rectangle as something that looks like a door, then it will be very difficult for them to change that. A further activity that I think might be useful to see the relationship that a square is a rectangle, but not the other way around, is to ask them, can we change the square into a rectangle? And by dragging the square onto the rectangle, they can see that it is impossible, no matter how much they try. You cannot turn the square into the rectangle. But we can change the square, we can change the rectangle into a square. In other words, a square is a special rectangle. It's a special kind of rectangle. And I suggest that activities of this kind be given also for the other quadrilaterals, so that they can see that a square cannot be changed into a rectangle, but a rectangle can be changed into a square. And perhaps I need to make a point here that sometimes in the primary school, certainly in South Africa, I have seen, and I think it is possible in other countries too, I've seen textbooks, and I've heard teachers too, first introduce a square to students in the primary school, and then move to the rectangle, saying that a rectangle is really just a square that has been stretched out. Which of course is problematic, because it is now suggesting that a rectangle is a special square, which is wrong. It is a rectangle that can be changed into a square, not the other way around. So it is very important that this activity and the introduction at the early levels to the quadrilaterals is done in a careful, thoughtful way. I have other activities on my website, not all as detailed as this one, and I don't think these activities are perfect. You can see I have several different quadrilaterals here, but it is just a suggestion as a possible idea to address this issue. Let us move back to where we were earlier. To get back to an isosceles trapezium that we spoke about earlier, After engaging students in the activities that they were engaged in earlier at Van Hiele 1 and Van Hiele 2, visually and analytically exploring and discovering and explaining why the properties were true by symmetry, one can now get to the point where one asks them to summarize all the properties that they have discovered up to this point. And notice language is again important. What do we mean by at least one here, etc.? Why do I have this two distinct pairs of adjacent angles? I'm not going to go into details there. But this formulation part is an important part of mathematics as well. But when they have reached this point, we can now ask them the following question. How would you, for example, over the phone, and because students use cell phones a lot, how would they, via SMS, because it is expensive for every character that you use, explain what an isosceles trapezium is to someone that has not yet seen it? And, of course, the suggestion that you try and keep it as short as possible because it costs money, I think helps a little bit. Perhaps also asking them, well, not perhaps asking, suggesting that they test their description by making a construction in dynamic geometry according to the conditions contained in it, and to test it to see if it actually works. And to try maybe formulating other ones and to test them as well. And perhaps also then eventually, can you prove, using logical deduction, that in fact all the other properties not listed can be deduced from the descriptions that you have used? Now I'm going through this very quickly. Of course, in a classroom, this would be, I would think, several periods of work, sessions, or a very long session if one were to deal with it with school children. But let me give you some examples of the sort of thing that one would do. If students came up with the following as a possible definition, then one could test that as a definition. And if students, by the way, do not come up with this, it's a good example that you as the teacher can suggest as a possible one and to examine it. An isosceles trapezium is any quadrilateral with equal diagonals. And I know students sometimes come up with this. I have examples of that. Now, we now want to construct, to test this definition, we want to construct according to what is given, a quadrilateral that meets the given conditions. So we start by constructing a diagonal. We choose an arbitrary point B and then draw a circle with the same radius as AC, which I have done there. Then we construct the radius BD, and we can see there that AC is equal to BD because that's how I have constructed it with the technology. And of course, all I now need to do is connect up the vertices to have my quadrilateral. And there's a quadrilateral that meets the given condition, meets the premise, as it were, if we wanted to. But the question is, does it always remain an isosceles trapezoid as I drag? If I now drag, you can see it does not, it is sometimes, yes, but it is not always an isosceles trapezoid. We have a figure here that is clearly not the mental image that we had earlier, doesn't conform to that mental image, nor does it have the properties that at least one pair of opposite sides always have to be equal, and so on. So clearly, this is a necessary condition, but not a sufficient condition for a quadrilateral to be an isosceles trapezium. It is not possible, I think, to deal with definitions without dealing with necessary and sufficient conditions. And it comes naturally when they can test their definitions with construction and measurement.